Good morning. This is the second lecture on steam turbine. Today I'll discuss on compressible flow through a nozzle. Contents of the lectures today are flow through nozzle. I'll start with introduction, then thermodynamic relations of flow of perfect gas, isentropic flow of perfect gas in a nozzle, isentropic flow of gas or vapor in nozzles. Then I'll discuss on convergent nozzle, convergent divergent nozzle, and effect of friction. Regarding introductions of steam turbine and nozzle, I like to say that the steam turbine is a prime mover which continuously converts the energy of high pressure and high temperature steam. This energy conversion occurs in the following two steps. The step 1, the high pressure and high temperature steam is first expanded in nozzles and comes out at high velocity jets of steam. In second step, this high velocity jets of steam impinge on the impeller mounted to the wheel and get deflected and thus suffer a loss of momentum, producing torque. Thus, a steam turbine is an assembly of nozzle and the rotating blades. Here, the flow of gas or vapor through nozzle is reviewed in brief. The past development of steam turbine and nozzles is very interesting. Most of the activities were centered in Europe and England. In 1878, a Swedish engineer, Charles G. P. de Laval, developed a simple impulse turbine using a convergent divergent supersonic nozzle. In 1897, he constructed a velocity compounded impulse turbine. Auguste Reynaud in France started experiments with de Laval turbine in 1894, and he developed a pressure compounded impulse turbine in 1900. In US, Charles G. Curtis presented the velocity compounded de Laval turbine in 1896 and transferred his right to General Electric in 1901. In England, Charles A. Parsons developed a multi-stage axial flow reaction turbine in 1884. Most of the activities were in the era of 1878 to 1900. By this time, the steam turbines were developed. Regarding applications of steam turbine, I like to mention that steam turbines are employed as the prime movers together with the electric generator in thermal and nuclear power plant to produce electricity. Steam turbines are also used to propel large ships, ocean liner, and submarines. Further, they are used to drive power-absorbing machines like large compressors, blower, fans, and pumps. Let us consider some thermodynamic relation of flow of perfect gas, considering the flow is one-dimensional and steady. Let's begin with the continuity equation. The continuity equation can be written as rho AV is equal to constant. Rho stands for density, A is area, and V stands for velocity. Thus, this equation can be put in the differential form as d rho by rho plus dA by A plus dV by V is equal to 0. Then the equation of state can be given for perfect gas as P into small v is equal to RT. P stands for the pressure, small v the specific volume, and T means the temperature. Thus this equation can be put in the differential form as dP by P plus d small v by V is equal to dt by T. Or it can be written as dP by P plus d rho by rho is equal to dt by T. Similarly, the equation of motion for ideal, reversible and one-dimensional flow can be given as, which is the Euler equation, dP by rho plus V into dV plus G into dz is equal to 0. Now, if we neglect the elevation, then dG into dz can be put to 0. Thus, the Euler equation of motion becomes dP by rho plus V into dV is equal to 0. Similarly, the energy equation can be given as for steady flow per unit mass between the two state points 1 and 2 as H1 plus V1 squared by 2 plus Q is equal to H2 plus V2 squared by 2 plus small w. Here change in kinetic energy and potential energy are neglected. Thus H stands for the enthalpy, V is the velocity, Q is the heat added per unit mass. Similarly, W is the work transfer per unit mass. So this is the steady flow energy equation per unit mass. Now, in absence of shaft work and adiabatic flow, I can say small w equal to 0 and Q is equal to 0, and thus the energy equation becomes H1 plus V1 squared by 2 is equal to H2 plus V2 squared by 2. Thus, I can define total enthalpy of stagnation enthalpy H0 as H plus V squared by 2, and thus stagnation temperature T0 as T plus V squared divided by twice Cp. Thus, from this equation, in absence of shaft work and for adiabatic flow, I can write H01 must be equal to H02. And if we consider Cp is constant within the range, then T01 total temperature at the state point must be equal to total temperature at state point 2, that is T01 equal to T02. Further, I've stated here the relation between the static and stagnation quantities, which can be expressed as P0 divided by P is equal to T0 by T to the power gamma by gamma minus 1. The Mach number I can define at a point M as V divided by A. V is equal to local velocity and A is the local sonic velocity, where A is given by root over gamma RT, and thus I can say T0 by T is equal to 1 plus gamma minus 1 by 2 m squared. All this relation which I have presented here has already been expressed earlier. However, I have reviewed again. Again, with respect to static and stagnation quantity, I can say that P0 by P is equal to, within bracket, 1 plus gamma minus 1 by 2 into m squared whole to the power gamma by gamma minus 1. So this is a relation of ratio of total pressure by static pressure with respect to Mach number, where I can say Cp minus Cv is equal to R, and Cp can be stated as gamma R divided by gamma minus 1 using the relation Cp by Cv is equal to gamma. Now from Euler equation of motion, that is reversible and adiabatic flow, I can write dP by rho plus dV into dV into dV is equal to 0. Again, let me say dP by rho plus V into dV is equal to 0. Now, this equation can be put in the form dP divided by rho into V squared plus dV by V is equal to 0. Now look here, rho V squared I can put in the form rho within the bracket V squared by A squared. Now A squared is nothing but gamma RT. Now B by A is a Mach number, so it can be written rho into m squared into gamma. Now RT is equal to P by rho using perfect gas equation. Therefore, rho V squared becomes gamma m squared into P. Thus, this equation becomes 1 divided by gamma m squared into dP by P plus dV by V is equal to 0. Thus, I can put the Euler equation in the form dV by V is equal to minus within bracket 1 by gamma m squared into dP by P. Now m is always positive, m squared. Therefore, as pressure decreases, the velocity would increase and vice versa. Again, from the continuity equation, assuming one-dimensional flow, we have d rho by rho plus dA by A plus dV by V is equal to 0. Now, the isentropic relation for a perfect gas can be expressed by PV to the power gamma is equal to constant, which can be put in the form dP by P is equal to gamma into d rho by rho. Now d rho by rho in the continuity equation can be replaced using the isentropic relation. Thereby the continuity equation becomes 1 by gamma dP by P plus dA by A plus dV by V is equal to 0. Thus, we can write dA by A is equal to minus dV by V minus 1 by gamma dP by P. Now, I have already proved that dV by V is equal to minus within bracket 1 divided by gamma into m squared into dP by P. Thus, from here, if I put the value of dP by P, I'll get dA by A as minus dV by V plus m squared into dV by V. Thus, I have got dA by A is equal to minus dV by V within bracket 1 minus m squared. Again, I can replace dV by V in terms of dP by P using this equation. Thus, I can express the continuity equation as dA by A is equal to dP by P within the bracket 1 minus m squared divided by gamma into m squared. Thus these two equations, which are dA by A is equal to minus dV by V within the bracket 1 minus m squared, or dP by P within the bracket 1 minus m squared divided by gamma into m squared, are very important, and the physical implications of these two equations will be explained in the next slides. I have derived these two equations, that's dA by A is equal to minus dV by V within bracket 1 minus m squared, and dA by A is equal to dP by P within the bracket 1 minus m squared divided by gamma into m squared. When m less than 1, that is flow is subsonic, then 1 minus m squared is positive. That is, when dA is greater than 0, dV is less than 0, and dP is greater than 0, and vice versa. That is, as area increases, velocity decreases, and thus the pressure increases. And for supersonic flow, when m greater than is equal to 1, then 1 minus m squared is negative. That is, when dA is greater than 0, dV is greater than 0, and dP is less than 0. That means for supersonic flow, as area increases, the velocity increases and pressure decreases, and thus vice versa. What I have stated earlier has been summarized here. Case 1, when the inlet velocity is subsonic, the pressure decreases and velocity increases with reduction of flow area, and vice versa. So, in a subsonic flow, a convergent passage acts as a nozzle, while a divergent section acts as a diffuser. Please note the figure here. For the subsonic flow, I have taken a convergent section. I have illustrated that at inlet, when M1 is equal to 0.2, at exit M2 would be equal to 0.4. Thereby, this is acting as a nozzle where the velocity has increased and the pressure has decreased with decrease of cross-sectional area. So, it can be stated as a subsonic nozzle. Similarly, for a subsonic diffuser, as the area increases, the velocity decreases, and thereby pressure increases. So suppose at inlet, if M1 is 0.7, at exit M2 would be 0.3, and the pressure would increase. Case 2, when the inlet velocity is supersonic, the pressure increases and the velocity decreases with reduction of cross-sectional area and vice versa. So for a supersonic flow, a convergent passage is a diffuser, while a divergent passage acts as a nozzle. Thus, I have illustrated here a convergent section where inlet Mach number is 3.2, the exit Mach number would be, as an example, 2.4, and the pressure also increases. Therefore, for a convergent section, it's a diffuser. So I have stated here a supersonic diffuser. Similarly, if we take a divergent section and the inlet speed is supersonic, suppose if M1 is 1.8, then M2 would be equal to 3.2. Therefore, for this divergent section, For supersonic flow, the speed of air, suppose, has increased. Therefore, the pressure has decreased. So this will act as a nozzle. So I have stated here this divergent section as supersonic nozzle. The conventional definition of nozzle and diffuser has got reversed in case of supersonic flow. This is because that in supersonic flow during expansion, the change of density occurs so fast that we need to have a divergent section to accommodate the fluid. Further, from the earlier equation that we have proved, I can say when dA by A is equal to 0, M is equal to 1, the section where the Mach number becomes unity is called the throat. Now I'll discuss about convergent divergent nozzle. Please note that a convergent divergent nozzle is needed to generate the supersonic steam, because in a nozzle the speed of flow can be maximum of Mach number 1 at the throat. Thus, the discharge through the nozzle becomes maximum when the Mach number at the throat in a convergent divergent nozzle becomes unity. And it is said that the nozzle is choked. Under this condition, it is incapable of allowing more discharge even with a further decrease in exhaust pressure. The property at the throat when the nozzle is choked are referred to as critical properties, and thus the discharge is known as critical discharge. Here I will discuss about a convergent divergent nozzle. Let us consider a closed chamber having a pressure P0 and temperature T0, which is connected to a convergent divergent nozzle. For a design pressure, which is called PE, one can see that pressure in the nozzle would continually fall, and the Mach number in the converging section will be subsonic, while the Mach number in the divergent section will be supersonic, and thus Mach number at throat will be unity. Now once this condition is reached, if we decrease the exit pressure further, the discharge would not increase in the nozzle. Thus, I have plotted here for the design exit pressure the distribution of pressure within the nozzle and the distributions of Mach number. One can see the Mach number is continually increasing while the pressure is continually decreasing in the nozzle, and at the throat Mach number becomes 1. So thus, what I told earlier, that to get a supersonic steam, you will have to have a convergent divergent section. So far I have discussed isentropic flow of a perfect gas through nozzles. Now I'll like to discuss flow of a gas which is not perfect or vapor through nozzle. Now let us consider a convergent divergent nozzle where the inlet section is represented by 1, 1 and exit section is represented by 2, 2, where V1 be the inlet velocity and V2 be the exit velocity, and so as H1 and H2. Thus, from steady flow energy equation for adiabatic flow, Without external work, we have h1 plus v1 squared by 2 is equal to h2 plus v2 squared by 2. From here I can get v2 is equal to root over twice h1 minus h2 plus v1 squared, where v1 is the approach velocity, v2 is the exit velocity, and h1 minus h2 represents the top of enthalpy within the nozzle. In reality, the approach velocity v1 is small compared to the exit velocity of the nozzle and is often neglected. Therefore, v2 can be expressed as root over twice h1 minus h2, which is the equation number 4. The enthalpy drop can be directly obtained from the molar diagram if we consider the flow is isentropic. The molar diagram is presented here, which is HS diagram, that is enthalpy and entropy diagram, where the saturation line is indicated by green, and I have also presented the constant pressure line P1 and P2. Now the state point 1 and 2 also has been marked, and H1 minus HT I have represented here, and one can easily appreciate that from molar diagram one can evaluate H1 minus H2. Otherwise, from the definition of enthalpy, we can write H is equal to U plus P into V, thus dH is equal to du plus P into dV plus V into dP. du plus P into dV can be represented as del Q, thus dH is equal to del Q plus V into dP. Now for adiabatic flow, del Q is equal to 0, thus we get dH is equal to V into dP. Hence, after integrating, I can write H1 minus H2 is equal to minus integral 1 to 2 into dH is equal to minus integral 1 to 2V into dP, which is the equation number 5. Thus, from equation number 5, one can evaluate drop of enthalpy, and this the value of H1 minus H2 can be put in the equation 4 to get V2. The function of a nozzle is to expand the flow, that is, the pressure will drop. For the adiabatic and frictionless flow of gas or vapor, we can represent the process as PV to the power n is equal to constant, where n is the adiabatic index. Now, I have considered a PV diagram where the process is represented by this line, which can be considered 1 and 2. So thereby PV to the power n is equal to constant is represented by a line as indicated here. Now, the integral minus V into dP can be represented as the area A, B, C, D in the PV diagram. Now the question is how I'll evaluate that integral minus V into dP, which is the area A, B, C, D in the PV diagram. Let me explain. Let me take a pen. So what I have told, 1, 2 indicate the process PV to the power n is equal to constant, and at any point V, let us consider dP, which is presented by a hatch region, is the change of pressure. Thus, V into dP indicates the area represented by the hatched region. Now I'll have to evaluate integral V into dP. Now let us consider P1 be the pressure at one step, and at the end of the process P2 be the pressure. So to evaluate this integral V into dP, which is the area ABCD, that means if I represent the area ABCD is indicated by a region bounded by the curve PV to the power n within the pressure P1 and P2. Now I'll divide the curve in three regions to evaluate the shaded region indicated by green. How? I can consider this one area. Let me take red. I can consider this region, which is represented by red. And I can subtract another region. Let me take a yellow color by this. So I land so hope I have been able to make you understand how we will calculate the area ABCD. Thus, integral minus V into dB is equal to P1 V1 minus P1 V1 minus P2 V2 divided by n minus 1 minus P2 into V2. Thus, if you follow this different shaded portion, you will realize how I have evaluated integral V into dP. So thus minus integral V into dP would be n divided by n minus 1 within bracket P1 V1 minus P2 V2, which would be equal to n divided by n minus 1 P1 V1 within the bracket 1 minus P2 by P1 to the power n minus 1 by n, which is represented by the equation 6. Thus, following earlier equations 4 and 5, I can get V2 is equal to root over twice n divided by n minus 1 P1 V1 within the bracket 1 minus P2 by P1 to the power n minus 1 by n, which is equation number 7, where n is the adiabatic index. Now for a perfect gas, n will be replaced by gamma. Thus for a perfect gas, we have V2 is equal to root over twice gamma divided by gamma minus 1 P1 V1 within the bracket 1 minus P2 by P1 to the power gamma minus 1 by gamma, which is the equation number 8. Now from the continuity equation we had m dot is equal to rho 2 A2 V2, where subscript 2 represents the any section of the nozzle. This can be stated as A2 capital V2 small v2. Capital V2 represents the velocity Small v2 is the specific volume. Now, equation 5 gives now the discharge per unit area, that is m dot by A2 would be equal to 1 by small v2 into root over twice 8 by n minus 1 p1 v1 within the bracket 1 minus p2 by p1 to the power n minus 1 by n. How we have arrived at? From this equation of continuity, m dot by A2, I can get V2 by small v2. Now, the V2, which is the velocity, we can get from equation 7. Thus, combining continuity and V2, I can get m dot by A2, which is equation number 9. Furthermore, from the relation PV to the power n is equal to constant, we have P1 V1 to the power n must be equal to P2 V2 to the power n. Thus, V2 is equal to P1 by P2 to the power 1 minus n into V1. Thus, here I can put the value of V2. Now, substituting the value of small v2 in the equation 9, we have m dot divided by A2 is equal to root over twice n divided by n minus 1 into P1 V1 within the bracket P2 by P1 to the power 2 by n minus P2 by P1 to the power n plus 1 by n, which is equation number 10. Now look here, P1 and V1 be the inlet pressure and volume, which is considered as a known quantity, and P2 by P1 is the pressure ratio. Thereby, mass flow rate through the nozzle would depend on the pressure ratio. Let us consider P2 by P1 is equal to Y. Now, for the maximum discharge, I can write d dy within the bracket y to the power 2 by n minus y to the power n plus 1 by n is equal to 0, which gives y is equal to 2 divided by n plus 1 to the power n divided by n minus 1. Thus, the critical pressure ratio for which discharge would be maximum is given by P2 by P1 critical is equal to 2 divided by n plus 1 to the power n by n minus 1. P2 be the pressure at any section of the nozzle, while P1 be the inlet pressure. Thus, the critical pressure ratio is given by the equation number 11. Just to remind you, the pressure ratio P2 by P1 for which the discharge becomes maximum is known as critical pressure ratio. The critical pressure ratio P2 critical occurs at the throat of the nozzle where M2 becomes unity and the nozzle is said to be choked. Furthermore, PT by P1 or P star by P1 is equal to 2 divided by n plus 1 to the power n divided by n minus 1, where PT or P star is the throat pressure. Now, the value of n can be given for different situations. N is equal to gamma is equal to 1.4 for diatomic gases such as air. N is equal to 1.3 for superheated steam. N is equal to 1.135 for dry saturated steam. Similarly, for wet steam, the value of N can be considered as 1.1035 plus 0.1 into x, where x being dryness fraction. Now for an example, when n is equal to 1.3, Pt becomes, that is throat pressure would be 0.546 P1. For n is equal to 1.4, the throat pressure would be 0.528 P1. Thus, through this example, one can appreciate that throat pressure or P star depends on the value of n, that is expansion index. Considering the knowledge we gained regarding isentropic flow of gas or vapor through nozzle, I have given an example for a convergent nozzle. So I have indicated here a convergent nozzle where inlet pressure be P1 and the exit pressure, which is the back pressure PB, is controlled by a throttle bulb. I have illustrated here the mass flow rate as the pressure changes, that is, as the back pressure changes. So I have indicated here the mass flow rate with respect to the back pressure, where back pressure is represented by a ratio PB by P1, where P1 being the inlet pressure. This indicates that as back pressure is decreased, the mass flow is increased, and at a certain back pressure, mass flow becomes maximum, which is m star, that is critical mass flow rate. After that, even if we decrease the back pressure, the mass flow would not change. However, the equation 9 gives the change, which is represented by dotted line. So dotted line indicates the theoretical mass flow rate through the nozzle. However, in practical situation, the flow is indicated by the form line, which illustrates that with decrease of back pressure, mass flow will increase, and when back pressure would be is equal to P star, then mass flow would be maximum, which is represented by m star. After that, mass flow would not change. So this I have summarized here. I have indicated that for a convergent nozzle, the discharge becomes maximum when the critical pressure is reached at the throat and the nozzle is choked. If the back pressure is reduced beyond the critical pressure, no further increase of discharge occurs. I'll continue with a convergent nozzle. Here I'll derive that for a perfect gas, the sonic speed is reached at the throat. I have already shown you the expression for velocity at any section of the nozzle where pressure is P2. Thus V2 is given by root over twice n divided by n minus 1 P1 V1 minus P2 V2, which can be expressed as V2 is equal to root over twice n divided by n minus 1 P2 V2 within the bracket P2 by P1 to the power 1 minus n by n minus 1, which is the equation number 13. Now, we know for the critical pressure ratio, P2 by P1 is equal to twice divided by n plus 1 to the power n by n minus 1. Thus, substituting the value for critical pressure ratio in the equation 13, we have V2 is equal to root over N into P2 small v2, which is equation number 14. Thus, for a perfect gas, the V2 can be stated as, here N would be replaced by gamma, thus V2 would be equal to root over gamma P2 into small v2. Now P2 into small v2 can be replaced by R into T2, thus V2 would be equal to root over gamma R into T2, which is the local sonic speed at any section of the nozzle or at the section 2 in the nozzle, which might be considered as throat. Hence, for perfect gas, the sonic speed is reached at the throat. I have indicated here a convergent nozzle where P1 be the inlet pressure and PB be the back pressure, which can be controlled. Let us consider the design exit pressure PE, for which the Mach number at the throat becomes unity and the nozzle is choked. Thus, I have indicated the distribution of pressure within the nozzle when the back pressure is equal to PE and the Mach number becomes unity. Now, if the back pressure is greater than PE, then the pressure distribution indicated by blue line, where it is a subsonic expansion. Now, when back pressure would be less than PE, now the pressure drop within the nozzle would be same as the back pressure would have been equal to PE, and the Mach number at the exit would be equal to 1. However, the pressure drop occur outside the nozzle in this case through expansion fan. Now let me consider the convergent divergent nozzle. For a convergent divergent nozzle, the discharge is maximum when the pressure at the throat is equal to the critical pressure P star. Suppose the back pressure PB is such that the isentropic flow prevails throughout and the divergent part acts as a supersonic nozzle with a continual decrease of pressure and increase of velocity. In such case, the back pressure PB is called the design pressure, which is designated as PE. Through a schematic, I'll illustrate now what happens in a convergent divergent nozzle when the back pressure is changed. Let us assume P1 be the inlet pressure, while PB is the back pressure in a convergent divergent nozzle, while PB can be controlled through a throttle valve. I have also illustrated the pressure distribution within the nozzle, where the pressure within the nozzle is represented by P by P1 and X be the distance along the center line of the nozzle. Now, when the back pressure will be equal to the design pressure PE, then there will be isentropic flow throughout the nozzle and the pressure will continually fall, where the velocity would continually increase and will get the supersonic flow within the divergent part of the nozzle, where P at the throat would be equal to P star and discharge in the nozzle would be equal to the M star, which is the critical discharge. The state point is represented at the exit of the nozzle is represented by 1. Now, if the back pressure is increased, then the design pressure PE. That means, let us consider the situation when PB is greater than PE by the state point 2 and 3. Then the shock will form within the nozzle, and after the shock, the flow would be subsonic. And as the back pressure would increase, the shock would travel upstream. Suppose when back pressure would be P3, then the shock will form here instead of here. Now for a situation when the back pressure is much higher than PE indicated by P5 here, then even the flow within the divergent nozzle will be like a venturimeter. That means the pressure would increase in the divergent part and the flow will be subsonic throughout. So the situation where the back pressure is greater than PE and where the shocks form inside the nozzle is referred as overexpansion. Now when PB is less than PE, then drop of pressure occurs outside the nozzle through expansion fan, and this is referred as underexpansion. So I have illustrated overexpansion and underexpansion in a convergent divergent nozzle for different back pressure. And please, when back pressure is greater than the design pressure, the shock may occur inside the nozzle. And please also note when the back pressure is less than design pressure, there will be drop of pressure outside the nozzle through expansion fans, which is called underexpansions. What I have explained earlier has been summarized here. When the back pressure is greater than the design exit pressure, shock occurs inside the nozzle and the flow becomes subsonic after the shock. The situation is referred as overexpansion. Further, for a back pressure, PB is equal to P5 as indicated here. Mach number is less than 1 at the throat, and the flow throughout the nozzle is subsonic with a decrease in velocity in the divergent part like a venturimeter. When PB is less than PE, a drop of pressure occurs outside the nozzle through a sudden expansion, which is referred as underexpansion. Again, for a convergent divergent nozzle, the divergence part of the nozzle must not exceed a certain value of equivalent angle of divergence due to the danger of flow separations. Hence, the length of the divergent part is considerably larger than the convergent part, which is in general short. Furthermore, the velocity in the divergent part is high. Thus, the flow losses is much greater in the divergent part than the convergent section. Now, we are considering the non-isentropic expansion of gas or vapor through the nozzle. As explained earlier, the effect of friction is predominant in the divergent part of the nozzle. Thus, the aerodynamic loss in the convergent part of the nozzle is often neglected as compared to the divergent section. Hence, the total loss of the nozzle is considered because of aerodynamic loss in the divergent section. Now, the enthalpy drop decreases because of aerodynamic friction, increasing entropy during the expansion of vapor inside the nozzle. Further, the dryness fraction of steam increases due to non-isentropic expansion. It should be noted that although the expansion in a nozzle is not isentropic because of friction, it may be considered adiabatic considering the fact that expansion is a faster process and the heat transfer from the nozzle may be neglected. Now let me define the nozzle efficiency. Before that, I'll consider the expansion of a combustor gas and that of steam through a convergent divergent nozzle. The TS diagram represents the expansion of a combustor gas, where P1 be the inlet pressure to the nozzle and P2 be the exit pressure, and 1, 2 be the actual expansion, where 1, 2s be the ideal expansion or isentropic expansion. Now from this figure, that is TS diagram, one can easily appreciate that enthalpy drop because of friction has decreased. Furthermore, consider the stream where P1 be the inlet pressure and P2 be the exit pressure, and here also 1 and 2 be the actual expansion, 1 and 2s be the isentropic expansion. Hence, because of friction, dryness fraction is increased apart from drop in enthalpy. Thereby, I can write nozzle efficiency as actual enthalpy drop divided by isentropic enthalpy drop. Hence, eta n is equal to H1 minus H2 divided by H1 minus H2s is equal to V2 square minus V1 square divided by V2s square minus V1 square. Now often V1 is neglected as comparison to V2. Thus this can be approximated as V2 by V2s whole square. Thus nozzle efficiency is represented by the equation 16, where V1 be the inlet velocity, V2 is the exit velocity from the nozzle, and V2s be the isentropic exit velocity. The coefficient of velocity of nozzle can be expressed as CV is equal to actual exit velocity divided by isentropic exit velocity, that is CV is equal to V2 divided by V2s. So this can be expressed by root over eta n. So CV can be given by the equation 17. Similarly, coefficient of discharge is given by CD equal to actual discharge divided by isentropic discharge. So it can be stated as CD equal to M2 dot divided by M2 dot isentropic, which is represented by M2s. Now, if we can assess eta n, that is nozzle efficiency. And if we know the isentropic conditions, then the actual exit velocity of the nozzle can be given by V2 is equal to root over twice H1 minus H2S into eta n, which can be expressed by the equation 19. Thus, here I have defined CV, CD, and V2 in terms of eta n. In this chapter, I have discussed about convergent and convergent divergent nozzle. I have discussed overexpansion and underexpansions on different formulation illustrating the discharge and velocity within the nozzles. Thank you for listening.